Hello there. In this video, I'm going to do the first part of section 14.3, which is about right triangles and trigonometric ratios. By the end of this section, we will understand how to apply trig functions like sine and cosine and tangent in ways that feel like they're finally leaving the xy plane and set up in more flexible ways that will allow us to do lots and lots of problems. But let's start with a motivating problem. Consider the point P with coordinates 4, 3. So here are the things that I want you to do. First, draw a rough graph of the x-axis and y-axis with the location of P. Figure out how far is P from the origin, and I have a hint there. Draw an angle in standard position so that the terminal side of that angle goes through P. Call that angle theta and give a rough estimate of how big you think it is. And then see if you can figure out what is cosine of theta and sine of theta. So hit pause and actually try this. I hope you have done that.
Check out the customer rate.
Okay. All right, sorry about that. Someone came into the room for a second. So I will draw my picture. Here's my x-axis. Here's my y-axis. 1, 2, 3, 4, 1, 2, 3, and P is somewhere around here. Now, if I want to know how far is P from the origin, the clever thing that I can do is I can draw a right triangle. I can go straight down here, over like so. And I basically want to know how far is that side. If I travel along this hypotenuse, I am finding the distance between the point P and the origin. Now we know P has coordinates 4, 3. So that means that this distance down here is 4. This distance here is 3. So if I wanted to find the length of that hypotenuse, I'm just going to call it h for hypotenuse. I know that 3 squared plus 4 squared equals h squared. 9 plus 16 equals h squared, 25 equals h squared, and h equals 5. So the distance there is 5. Now, given what I've already done here, it's pretty easy for me to extend this into an angle in standard position. Here's one side following the x-axis. Here's the other side. Basically already hinted at it. And here is my angle theta. I'm actually going to delete this part because it's kind of getting in the way. There's my angle theta. It looks like to me theta is something like 40 degrees. That's just my rough approximation from the picture. Now, what if I want to figure out cosine and sine? This is where things get a little tricky. Cosine and sine we know how to do in terms of the unit circle, but we don't really have the unit circle in this picture. But here is the trick. What we're going to do is we're going to add the unit circle within our diagram and look for a smaller triangle that's similar to the one we've already drawn. So here's what I'm going to do. I'm going to redraw this picture. Let me make this a little bit higher. I'm just going to draw the positive x and y axes. So 1, 2, 3, 4, 1, 2, 3. Our point P is up here. And we've already focused on this angle in standard position. I'm actually going to put this segment back. Well, what if I add the unit circle to this diagram? Here's the unit circle like so. And I'm going to cheat a little bit so that this looks like this is at 1, 0, this is at 0, 1. So the point P is way out here. And we have this angle theta. There's the angle theta. What we can realize is that if we are clever, I can add another triangle in this diagram, like so. So there's a triangle I've made in that greenish yellow highlighter. There's the triangle I've made in the pink highlighter. Those are similar triangles, which means they're exactly the same shape. One is just bigger than the other. So let's think, what do I know? I know that this entire distance here is 5. I know that this is 3, and I know that this is 4. For this little triangle inside, I'm just going to draw a separate version. I'll try to draw it exactly the same size. Here's my smaller version. I know that because this is a unit circle, by definition, this hypotenuse is 1. So what we might notice is that the hypotenuse of the little triangle is 1/5 as long. But this is a similar triangle. If the hypotenuse is 1/5 as long, then the other sides are 1/5 as long. So that means that this base down here, the horizontal leg at the bottom, is 1/5 as long as this one. Well, if this is 4 and this is 1/5 as long, this one is 4/5. Similarly, in the bigger triangle, the right-hand side has a length of 3. If it's 1/5 the size, this one is 3/5. So that means this point right here, we went over 4/5, we went up 3/5. And what we'll discover is that cosine of that angle is 4/5. Sine of that angle is 3/5. So even though we weren't starting with a point on the unit circle, if we knew the coordinates of this point and we're still thinking about an angle in standard position, there is a way of figuring out sine and cosine. It's not as simple as cosine is x and sine is y. The x coordinate was 4 and the y coordinate was 3. We divided both of them by 5. And if we trace back, 5 was measuring that distance. How far is P from the origin? So we could repeat this for pretty much anything. So that's what I say here. We could repeat this process with any point. So it's probably best to just remember the pattern. So here is the key concept you want to keep in mind. Trigonometric ratios for a circle, even if it's not the unit circle. That's what all of this is going to be. Right? This is all one big concept. So here's our setup. Suppose the angle theta is in standard position and the point xy is on the terminal side. I'll draw a generic picture down here. Here's my x-axis. Here's my y-axis. I'll draw an obtuse. Let's suppose here is the point P. I'll put it in the second quadrant. Here is my angle in standard position. We'll call that angle theta. So there's our setup. We'll let R measure the radius of the circle passing through that point. Oh, I guess I'm just calling it xy rather than P. I'll just call this xy. R would be the radius of this circle that goes through that point. So R is basically measuring this distance here. R is measuring that distance. If you draw a triangle, that's the hypotenuse of a triangle. Right? You might imagine, oh, if I draw this side and this side, I get a triangle. This is an R. So R measures that distance. You can get it by the Pythagorean theorem. If you want to just remember the shortcut, R is the square root of x squared plus y squared. And I'll remind you that even if x or y is a negative number, x squared and y squared are positive. We're always dealing with positive numbers in that formula. So how do we find sine and cosine? Well, let's look at what we did here. Here we found cosine by taking the x coordinate like we would on the unit circle, but we divide it by r. If it's not the unit circle, you have to divide. We found sine, same way, y coordinate divided by that distance r. So that's what we're doing here. Cosine is x divided by r. If it's not on the unit circle, you have to remember to divide. Sine is y divided by r. Tangent will be y over x. Cotangent will be, I have a typo here. Cotangent will be x over y. I'll fix that in my document. That's cotangent. Secant is r over x, and cosecant is r over y. So when we have some sort of picture like this, we don't need a unit circle. If we know x and y and r measuring this distance, we can find all the trig values that way. So let's practice a little bit. Suppose theta is in standard position and its terminal side passes through the point -5, 12. Compute cosine theta and cotangent theta. So let's draw a little picture. Right, and my numbers here are big enough that I'm just going to draw a rough picture. I'm just going to declare that here is -5, and here is 12, and here is our point. And our angle looks something like so. So the first thing I want to do is measure what is the distance r. I'll do it as a capital this time. If you imagine a right triangle in here, we basically have 5 squared plus 12 squared equals r squared. Don't get caught up on the fact that it's -5. This distance is still 5 no matter what. So we have 25 plus 144 equals r squared. R squared equals 169, and I actually cooked that up rather nicely so that we get r equals 13. So I know that x equals -5. Y equals 12, and r equals 13. So I have rules for this. How do I find cosine? Cosine is the x coordinate, but we have to remember to divide that by r. So it's -5/13. Cotangent is x over y. Let's double check that I have the correct version there. Cotangent would be x over y, which is -5 over 12. For the second one, I'm calling the angle alpha. This is the Greek letter alpha in lowercase. And it goes through -8, -15. Again, we'll just draw a rough picture and just kind of declare what those values are. Here's our point. So our angle in standard position, I'll draw it as a negative angle. Maybe it looks like this. There's theta. Right, hit pause and try to figure this out the same way. So I hope you did that. We need to figure out what r is. R will be the square root of x squared plus y squared. -8 squared is +64. 15 squared is +225. This works out to 289. And again, maybe you didn't anticipate this, but I set you up so that r is a whole number. So r is 17, y is -15, x is -8, and we just apply these formulas. Sine here, ordinarily sine is the y coordinate, but that's only on the unit circle. So here, sine of alpha is the y coordinate divided by r. And secant was r over x, which is 17 over -8. And typically, we don't like negatives in the denominator. You can just pull that out. So for these problems, you need to do a little bit of extra work to compute r, but all of the information is available to you. Now, we're going to do even more, because we want to apply this to other triangles. Not every triangle looks like it has a corner at the origin and we're following an angle in standard position. So here's something you want to keep in mind. Any right triangle is congruent. Remember from geometry, congruent means same size and shape although we may have changed the position or orientation. It's congruent to a right triangle like the ones we've seen. So here's sort of an example. Here is a triangle like the ones we've seen. I have a corner here at the origin. This hypotenuse is following the terminal side of my angle here in standard position. Here's the point xy. This is the y coordinate. It measures how tall the triangle is. This is the x coordinate. It measures how wide the triangle is. We've seen a lot of examples like this. What I want you to realize is that this triangle that I've drawn over here is the same size and shape of this one. The two red triangles are congruent. But I've moved it around in a way where we don't really want to talk about standard position or x coordinates or y coordinates, right? This is just a free-floating triangle without coordinates. But let's go back to what I'm saying. Instead of getting caught up in the particulars of x and y values, we should think about how the legs are related to the angles in question. And we'll use the phrases adjacent leg and opposite leg to talk about these relationships. So let's look over here. Right? Suppose that I wanted to find cosine of theta. In this example here, this is our standard picture, cosine of theta is x over r. And let's think about this. We're focusing on this angle theta. There's the angle theta here, there's the right angle here. This angle we're not talking about. So always keep in mind, where's the angle where we're actually talking about stuff? Here's the angle theta. This x is actually measuring a length in the triangle. It's measuring a leg. Right triangle has a leg, and a hypotenuse. And it's the leg adjacent to theta. Here's the angle theta, here's the hypotenuse, here's the leg that is right next to theta. So we're going to call this the adjacent leg. X is measuring how long is the adjacent leg. R is measuring how long is the hypotenuse. So if we go over here, we'll notice it's the same relationships, but I'm labeling it differently. Here is my angle theta. I no longer have x and y because I've moved this around. But we can think about what are the relationships. Over here, x was the top. But what was x? X was measuring the length of the adjacent leg. Here's the angle, here's the leg that is right next to it. Over here, here's the angle, here's the leg that is right next to it. Make sure you're not picking a hypotenuse. So the leg right next to that is what we just call the adjacent leg. By default, I'm just going to call that A for adjacent. I'll call it ADJ for now. Over here, cosine was x divided by r. X measures how long is this thing, the adjacent leg. R is the hypotenuse. Over here, here's the hypotenuse. I'm calling it just h for hypotenuse. So after I've moved this triangle around, we don't want to talk about x and y because that might not make sense. Instead, we want to look at this triangle and say, all right, well, here's the hypotenuse of my triangle. If this is the angle I care about, this is the leg that is adjacent to it. This is the leg that is opposite from it, right? It's as far away as possible. How about sine? Sine of theta in the original picture would be the y coordinate divided by r. That's perfectly fine, but once we move it around, we can't really talk about y coordinates. So we want to explore the same relationship. Well, what was y really measuring here? I called it y, but what y really is the leg opposite from theta. Go as far away as possible. How long is that leg? So over here, here's theta. This is the leg opposite from it. I labeled it here just as O for opposite. I'll write OPP here so it's a little bit clearer. The denominator in sine of theta is r. R is just what is the hypotenuse of that triangle. How about tangent of theta? Tangent of theta we would get by doing y over x. Tangent of theta over here, well, we don't really have a y and x. We need to remember what they stand for. Y is the leg opposite from theta. X is the leg adjacent to theta. So instead of saying y over x in a really particular way based upon coordinates, we can just say opposite over adjacent in a more general way. So we have sine of theta is equal to opposite over hypotenuse. Cosine of theta is equal to adjacent over hypotenuse. And tangent of theta is equal to opposite over adjacent. These relationships are often memorized in this nonsense word, SOHCAHTOA. Read these 3 letters at a time. SOH is just an abbreviation for sine is opposite over hypotenuse. CAH is just an abbreviation for cosine is adjacent over hypotenuse. TOA is an abbreviation for tangent is opposite over adjacent. I'm going to end this video here, but we'll practice more in the next part of the video.